This video is a solution to free response question number 3 from the 2016 AP Physics 1 exam. In this problem, there's a long track with a bunch of little bumps on it, and there's a cart with mass M that's released from the top of the track, and as it goes down, it collides with the bumps. The track is much longer than what's shown, and there's a student that notices after the cart gets to the 40th bump, the average speed between the successive bumps no longer increases and has a maximum value of V average. And after that, then the average velocity of the cart is constant, but still it's affected by the bumps that are on the track. For part A, it says to consider the cart's motion between bumps 41 and bump 44, which means that we've already reached the point where the average velocity of the cart has reached a maximum value. In the figure below, sketch a graph of the cart's velocity v as a function of time from the moment it reaches bump 41 until the moment it reaches bump 44. So what we need to do here is we need to recognize that every time the cart hits one of the bumps, the velocity is going to decrease, and then in the space between that bump and the next bump, the speed of the cart is going to increase again, and then will decrease by the same amount when it hits the bump again. And so each bump, the velocity is decreasing by some constant amount, but the average velocity over time, even over the course of these 4 bumps, needs to be some constant value which is equal to V average. So I'm going to start drawing the graph right around bump 41, and I know that at the bump the velocity needs to decrease, something like this. As I go across the bump, the velocity decreases, and then from the point after I've gone over that bump until I get to the next bump, the velocity of the cart needs to linearly increase. The velocity is changing, but at a constant rate due to the fact that the net force on the car is constant in between the bumps. When I approach the next bump, my velocity should decrease by the same amount, and then once again in between the 2 bumps, my velocity increases again. I get to the 43rd bump, my velocity decreases, and then once again my velocity increases as I approach bump number 44, where once again the velocity should drop back down. So since A1 said to sketch the velocity as a function of time from when it reaches bump 41 until it reaches bump 44, I think that this line does a good job of that. For part A2, over the same time interval, draw a dashed horizontal line at V equals V average and label this line V average. The most difficult part of this, I think, comes in the directions, because in the directions they say a student notices that after reaching the 40th bump, the average speed of the cart between successive bumps no longer increases, reaching a maximum value of V average. I feel like it's tempting in my graph to make the V average line be at the top of the points that I've drawn in the graph. But the V average line should be drawn somewhere right in the middle of everything that I've put here. Right about here. In the directions, when they say that the V average reaches a maximum value, this is the maximum value that they're talking about. And before I reach bump number 40, I might have had a smaller average velocity. And you can see that everywhere in my graph, if you look over the range of 1 or 2 bumps, then at some points the velocity is higher and at some points the velocity is lower, but V average represents the average velocity that the cart would have over a time interval that's shown. Part B says, suppose the distance between the bumps is increased but everything else stays the same. Is the maximum speed of the cart now greater than, less than, or the same as it was with the bumps closer together? The most important thing to recognize here is if I draw a little sketch of that track with the bumps. If the bumps are more spread out, then the distance between the bumps is becoming greater, and if the distance between the bumps becomes greater, then there's more space for the cart to speed up in between the bumps. And so if I keep everything else the same, but increase the distance between the bumps, we should find that the maximum speed of the cart is greater than what it was before. And that's simply for the fact that, the net force on the car is the same as what it was before, but now that net force, which causes the cart to accelerate, causes the cart to speed up, now there's more time for the cart to do that between successive bumps, and so we should expect a greater maximum speed. You could also argue that if the distance between the bumps is increased, that the change in the height between successive bumps is going to be greater, and if there's a greater change in height between successive bumps, like for example from the two bumps that I've shown there's a certain height difference in where each of those bumps are. If the change in height between the successive bumps is increased, then there's a larger change in gravitational potential energy between the two bumps, which means there would be a larger change in kinetic energy between the two bumps, and therefore there would be a larger maximum speed allowable by the new track. Part C asks a similar question, but says now, with the bumps returned to the original spacing, if the track were tilted to a greater ramp angle, theta, is the maximum speed of the cart now greater than, less than, or the same as what it was before? And once again, I think that the answer here should be greater than. We could use our previous reasoning for this. If I tilt the ramp angle up higher, as I've shown above for the question in Part B, the change in height between successive bumps will once again be greater than what it was before. And for that reason, there will be a larger change in potential energy, and therefore a larger change in kinetic energy. And so we should expect that once again, the maximum speed of the cart is greater than what it would have been at the lower angle. Also, if we increase the ramp angle, then the component of the force of gravity that would point down the ramp would be larger, and so there would be a larger net force and therefore a larger acceleration that acts on the cart. And for that reason as well, the maximum speed of the cart should be greater than what it was before. Part D says, before deriving an equation for a quantity such as V average for the track that we've been looking at, it can be useful to come up with an equation that is intuitively expected to be true. I feel like Part D is a very valuable sort of question to think about. They propose this equation. The V average is equal to some constant C times the mass times gravity times the sine of the angle of the ramp divided by the bump spacing D. To test this equation, the student rolls a cart down the track with the speed bumps many times in front of a motion detector, and the student varies the mass m of the cart, but keeps everything else the same. The graph that is shown below shows the average velocity of the cart as a function of the mass of the cart. And the question they ask is, are these data consistent with the student's equation? So we need to look up at the equation and see whether or not what we see in the graph is consistent with the equation. And the first thing that I would hope you would find is in the graph, it looks like the average velocity of the cart is proportional to the mass, meaning that as the mass of the cart was increased by the student in successive trials, the average velocity of the cart also increased. And if I look at the equation up above, the mass is in the numerator, and so the average velocity should increase as the mass increases. And so if we're trying to compare the graph to the proposed equation, so far it looks like those two things are in agreement. It is tempting to check yes because it looks like that relationship holds in the equation and in the graph. And looking at the rubric that the College Board provides, you can earn a point for checking yes and then giving an explanation that as I've said it here. But one thing I notice about the equation up above is if I were to double the mass, so let's say instead of m, I have a mass 2m, then I should expect that the average velocity also doubles. If you just look at the equation, if everything else stays the same, then we should expect that the average velocity doubles. But when I look at the graph and I go from the place where the mass was equal to 1, that's where the average velocity was equal to about 1.5. And then if I go to the place where the mass is equal to 2, I find that, maybe it's a little bit north of 2 meters per second for the average velocity, but it didn't make it all the way up to 3. And for that reason, it doesn't look like in the graph that the equation is going to exactly hold. There is a relationship between the average velocity and the mass, but it doesn't seem to be the direct linear relationship that was shown in the proposed equation up in the problem statement. The only way that that would work is if when I moved over to m equals 2, if the graph had been all the way up to about 3 meters per second, all the way up here, such that when I doubled the mass, the average velocity doubled. And so because of that inconsistency between the graph and the equation, I'm going to check no, the data are not consistent with the student's equation, and then I'm going to cite this difference between the graph and the equation. The last part of this equation asks, does the equation make physical sense? Which is another very valuable question to ask. So I look up at the equation. I can't say much about the positive constant, but I'm looking at the relationship between the average velocity and the mass, the average velocity and g, the average velocity and theta, and the average velocity and the distance between the bumps. And I'm checking to see, should any of those be in the denominator, or should any of those be in the numerator, but they're in the wrong spot? So for example, if the mass increases, I should expect that the average velocity increases, because the net force that acts on the cart would be larger if the mass were larger. The same thing applies for gravity. If gravity were stronger, then the net force acting on the cart would be greater, and therefore the cart should move faster. And so both of those things seem to be like reasonable things to put in the numerator of the equation. If I increase the angle and make theta larger, so for example, if I go from 20 degrees to 30 degrees, the value of sine theta is going to also get larger. And so as theta increases, the average velocity increases, and that's something that we supported with our argument to one of the previous problems. And so it seems like m, g, and theta should all be in the numerator. And then the last variable that's in the equation says that v average is proportional to 1 over d. And so the question is, as d increases, does the average velocity also increase? And we were asked about the separation of the bumps increasing in the previous problem, and what we found is if I increase the separation between the bumps, then there's more time for the cart to speed up, so the cart should move at a greater velocity. And our reasoning for that was either because there's more of a difference in height between the bumps, or because there's more time for the net force acting on the car to accelerate the car between the bumps. And so for that reason, as d increases, as the separation of the bumps between the carts increases, then I should expect that the average velocity increases. But if the value of d is in the numerator in the proposed equation, then the opposite is true. And so for part d2, I should check no. This equation does not make physical sense because d should not be in the denominator. An increase in d in the student's proposed equation would cause the average velocity to decrease instead of increase. A good part of the rubric that the College Board uses for this question states that, if instead of talking about d, if a student wanted to talk about the dependence of v average on the angle, then they could earn a point here, but full credit is only awarded if a student inspects all of the variables and notices that d is not in the correct place. Because regardless of whether or not theta is in the right spot, the equation doesn't make physical sense due to the fact that d is in the denominator.